Okay, so recall that the corollary to the fundamental theorem of algebra, I can't read it there, states that a polynomial equation of degree n has n solutions in the complex number system. What that means is this. If f of x equals like x to the n power plus dot, 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 then you have n solutions. So, for example, if I have degree 4, I should have 4 solutions. However, will all my solutions be real? Not necessarily. Will some be repeated? Yeah, that could happen. So, for example, what if n equals 4? If n equals 4 and your leading term is positive, what would the n behavior be? You guys remember n behavior? Up, up. Good. Yeah. Good, Mr. Brown. I'd be very happy to hear that. Okay, good. If you even miss, I wouldn't tell him. It's okay. All right. They have 4, right? 1, 2, 3. That's a 12. Those are 4 real answers, right? But it could look like this. That's fine, right? I have 2 real. So my other 2 solutions are. Yeah, and we're going to talk about that in the spring semester when we come back from Christmas break in January. We'll talk about that. Sure. Yeah, those are 2 of the imaginary. Right, that could happen. That's a possibility. Or you have that. How many complex solutions do I have? All 4 of them are imaginary, right? And by the way, imaginary solutions come in pairs, by the way. We'll have that discussion again in January sometime. And we'll start incorporating some calculus as well. Or I have this, right? So how many x intercepts do I have here? But this one bounces. So would it repeat? Yeah, that's multiplicity 2, and these have each have multiplicity 1. So that's what the fundamental theorem of algebra is telling us, right? Okay, so when x of 6 equals 1, this is a little deceptive. Because you think, well, just take the 6th root, right? What's 6th root of 1? Or negative 1. You know, because negative 1 raised to 6 power is still 1. Okay. But this is degree 6. So shouldn't it be 4 more solutions? And what would they? Square root. Yeah, they'll give me some wacky complex numbers. Yeah. Excuse me. Yeah, because what if I graphed y equals x is 6 minus 1, right? What if I graph that? It's going to look kind of like this, almost like a parabola. It's kind of flat at the bottom a little bit. It's kind of a weird graph, but the things that are still going to be 4 other solutions that we need. So we need a process to help us find that. And that's why we're going to take what we did from De Moivre's theorem and extend on that. Remember, example 8, I think we had like negative, the answer was negative 8, I think. Was that right? Or maybe it was, or it was number 7. Yeah. It was negative 8 for, yeah. And remember I said, what's the cube root of negative 8? You guys knew it was negative 2. But how can 1 plus I root 3 cube gets me that? Because 1 plus I root 3 is the cube root of negative 8, as well as 1 minus I root 3. So we're going to see that. Now, one thing to keep in mind, you don't have to copy this down, but one thing to keep in mind is that, isn't that the same thing as saying this? Right? And you probably don't remember this. Maybe you guys did this last year. I don't know. I got to talk to Mr. Ban. There's the difference of cubes formula. But you guys did it. Okay, good.
I forgot it.
We'll talk about it in January.
Actually, did talk about it.
Well, this can be broken down further. And if I solve this using quad form, I'll get imaginary answers. And I'll get imaginary answers. So now I know, now I see, okay, yeah, this should provide 6 answers. But I'm going to show you a process that kind of streamlines all this. Instead of like, because sometimes you don't have that luxury to break down the polynomials this way. Sometimes you don't have that option. So we need a more universal process that will always be reliable. So yeah, the 6 root of 1, I know it's plus or minus 1, but there's going to be 4 other answers. So here's the deal. We need to write um, whatever we're trying to find the roots of as a complex number. So is 1 a complex number? Actually, it is. 1 is a complex number, believe it or not. Actually, all numbers are complex numbers. It's just they don't have the BI, right? It's like saying 1 plus 0i. Is 1 plus 0i 1 still? Of course. So you could use this to help you. Now here's the formula. It's really funky. It looks super crazy. Don't worry. It'll make sense when we do an example. But this is the formula. I'll give it to you, by the way. And yes, there is K's. The K's do come out to the vengeance. We'll see. But if you try to find the root of a complex number, figure out what, put in the trig form, R, go say that sine theta, whatever, right? Do that. And then we have to find all the roots using k equals 0, k equals 1, k equals 2. You'll see in a moment why we're doing that. So let's find the 6th root of 1. And by the way, sometimes we call the 6th root of unity. Unity means 1, like unit circle. So here's what we're going to do. You have 1 plus 0i. So a is 1 and b is 0. So what's your r going to be? What's your magnitude of that complex number? 1. What's your theta here? Yeah, 0. Because when you plot it on the complex plane, isn't it right here? Is that angle just 0? Or if you did tan theta equals 0 over 1, what's that going to equal for theta? 0, yeah. There we go. Great. Okay. So now what you do is this. You're going to find we're going to call it this. Z1, Z2, Z3. Actually, I'm going to need a little more space here. Z1, Z2, Z3, Z4, Z5, and C6. So we're going to do the 6 roots of R times bracket cosine and you're going to do theta plus 2 pi k, 0 plus 2 pi k. So looking at the formula again, see how it says theta plus 2 pi k over n, theta plus 2 pi k over n, and you start with k equals 0. And you keep going until you exhausted all the k values. So because you have to do 6 roots, so what k value am I going to stop at then? Good. You're going to do 0, 1, 2, 3, 4, 5, right? And you just do this over and over and over and over again, and it'll give you each root without having to factor or plot form it or any of that crazy stuff. So 6 root 1, that's easy. What's 6 root 1? 1, right? And then up top, is that going to be 0 over 6 and 0 over 6? What's cosine 0? And what's sine 0? Great. So you have 1. You can get rid of this other stuff here. And actually, I could probably space this out a little bit better. Ah, so much better. There you go. Yeah, so it's gonna be 1 times 1 plus 0i, which of course is just 1. We know this. Not a problem. Okay. Same thing again. 6 root of 1 times cosine. So now I'm going to do 0 plus what? Plus 2 pi. And just think about it. 2 pi over 6, 4 pi over 6, 6 pi over 6, 8 pi over 6, and 10 pi over 6. Because I'm going to keep multiplying this 2 pi by every interval k until I've exhausted all 6 roots. So k equals 0, k equals 1, k equals 2, k equals 3, k equals 4, k equals 5. So for Z3, let me redraw it here. For Z3, and I'm going to get a little lazy here. You still let me copy and paste these. That's not letting me do that. That's weak. All right, let's do it over again here.
You have to show all this work.
Yeah, I do. Sorry.
So how long does a problem like this usually take on?
I do factor in when I do work out the final exam. I don't know.
How many groups like would you give us? Like more than 6?
How many you guys want?
Like,
You tell me.
I'll take it. I'll take it.
Oh, one root, just one root. How about we give Lucas like 8 roots and the rest of you guys get 3?
I'll take that.
Okay. Anyway, Luke's gonna ask a question, but it's okay. Actually, Lucas, you haven't asked me a question, so you okay, dude?
Yeah.
You good? Okay, okay. So make sure. Okay. All right, okay. Or maybe I'm just teaching it so well. Okay, so yeah, you can see it gets kind of nasty because you got pi over 3, 2 pi over 3, pi, and so forth. What's cosine of pi over 3? So I'm gonna have 1/2 plus root 3 over 2i. And that's going to be negative 1/2 plus root 3 over 2i. That's going to be negative 1. And you kind of get the idea now what's going to happen. We'll have negative 1/2 minus root 3 over 2i. And negative 1/2, sorry, positive 1/2. Because now you're in the 4th quadrant, right? So here's the other thing too. This actually ties very closely to unit circle. It's actually kind of a really neat example. I'll draw on the board. It all ties closely back to unit circle, right? Because if you think about it, that's 1 plus 0i. That's negative 1 plus 0i. That's 1/2. Solutions. You'd agree with that, right? Because how long is my radius here? As it should be, right? 1/2. And why do I have 6? So I have 6 roots. And what is separated by? How many degrees or radians? 60 degrees for pi over 3, right? So again, so that's why I kind of know what the other 2 answers is going to be. Because now I'm going to be in the 3rd quadrant. In the 3rd quadrant, A and B both negative. In the 4th quadrant, which one's positive, which is negative? A is positive, B is negative. Correct. So actually, I messed that one up. My apologies. That should have been minus. My apologies. That was messed up. That's another reason why we call it the six roots of unity. It comes from the unit circle as well. So actually, does it graph solution to the complex plane? I did it for you right there. I did it for you. In fact, actually, if you label it this way, and I give you like a quarter, or I give you like a unit circle, whatever. If you label like that, I'm good. You don't actually have to like do all the final labels. If you just put Z1, you just put in the right spots. I'm totally cool with that. So that's your graph right there. I already did a graph for you. And those are your answers. So that's an extension of DeMoss theorem. And if you were to raise this, by the way, any of the ones with like the eyes in them, if you were to go in your graphing calculator, if you go to TI-84 calculator and punch that and raise it to 6 power, it's going to say 1. It might say with a weird decimal like 0.999 or 1.01, or it might be like put a exponential, scientific notation next to the I with like e raised to negative 16 power or 10 raised to negative 16 power. Something it looks something kind of crazy. That's okay. It's 1. If you raise it to 6 power, you will get 1. Just so you know. Okay, questions. All right, let's try a fresh one. That graph, I just did it for you. Yeah, I already did it for you. Yeah, it's just a unit circle. Yeah.
Wait, so the radius of the circle is just what the root is doing?
Correct. Correct. And the angles you'll be able to separate because you'll know the angles. Like for example, if I'm doing third root, obviously they're separate by 120 degrees, right? So I'm going to separate by 120. All right, so this might be a little more reasonable. Cube roots, okay. So first, let's figure out R and it's not 0. What's R going to be? Root 8. We'll say 2 root 2. Theta. 3 pi over 4 because you're in the second quadrant. Good. Yeah, and by the way, you kind of have to do this in. You don't have to do it in radians. You could actually switch to degrees, but instead of multiply by 2 pi, then you got to do 360. If you do that, I won't hold it against you. If you want to, you totally can. You can do your own little Demois theorem with degrees. Go for it. But probably better to stick with what we have. Okay, let's do it. So you're gonna have Z1, which is kind of nasty. So you're using the cube roots.
Wasn't it you just read as the cube? What was it? You
Yeah.
read 8 and then
Yeah, or you could do this. Do you guys like that a little better? 8 to the 1/6 power. Because you're doing wait, does that make sense? Yeah, that makes sense. Yeah. Yeah, it is 8 to the 1/6 power. It's up to you. I don't care. It's your call. Cosine, you have 3 on the bottom, 0 plus oh, not 0. I'm tripping. What's your theta?
3 pi over 2.
3 pi over 4 plus 0 plus I sine. Actually, I like 8 to the 1/6 a little better. Looks cleaner. And of course, 3 pi over 4 divided by 3 is going to be pi over 4. Actually, before I approximate it, 8 to the 1/6 power cosine of pi over 4 plus I sine pi over 4. Well, cosine pi over 4 is root 2 root 2, right? I think I could probably try reducing it, but I don't know. I don't feel like it. Let's just get the decimal answer. So let's see here. 8 raised to the 1/6 power. It's crazy. It actually comes out as root 2. Is that right? Yeah. Oh, okay. Times cosine of 45 degrees. Oh, actually came out kind of nice. 1 plus I. Yeah. Yeah. Actually came out like that. It was 1 plus I. That was lovely. 8 raised to the 1/6 power. Cosine. Questions?
So on the test for these kind of problems, we have to use your graph.
You'll have one, yeah. Yeah. So that's 8 raised to the 1/6. Ugh. It's nasty. That's gonna be is that 11 pi over 12, I think? Yeah, it's 11 pi over 12. Yeah, that you can't, you need a calculator for sure. So you get negative 1.366. Plus 0.366i. And I'm just going to check my calculator if I raise that to the 3rd power. Yeah, you do get negative 2 plus 2i approximately close to it. So that's one of your roots. That's yet another root. And just double check if I do 1 plus I raised to the 3rd power. Yep, I get negative 2 plus 2i. Okay, good. Okay, and then the last one, I'm going to erase this one because I need some space here. So I'm going to put 4 pi, right? Let me think here. That's going to be if I do 8 pi over 4, so that's 16 pi over 4. Should be 25 pi over 12, I think. 19. You're right. You're right. Correct. Right. Oh, because you have 4 pi over 3. Right. So you got to multiply 16 to 9. Yes, 19 pi over 12 is correct. Yeah, it's just fractions. Cosine 19 pi over 12 times root 2. Yeah, it's reversed. It's 0.366. Is it minus 1.366i? Yeah, good. Yeah, good. Okay, cool. Those are your roots. Okay. So we're done with the complex number stuff. Now we're gonna get more with that. So these notes are gonna last the whole week.
Is that all we're doing with so do some are crazy in college.
Okay. Let me pull up. So Ms. York made these notes. They're really more just for us to talk about. There's not really too much for you guys to write out. I'm gonna get the homework for you in a moment. Trying to figure out how far I want to get today. Yeah, I think I'm gonna get to like maybe the 1, 2, 3, 4, maybe about half, well, maybe 4 pages. Yeah, we'll get about 4 pages, so or 5 pages. Yeah, that should work. Okay, cool. Let me pull up our notes here. Everyone downloads. There we go. All right. Okay. So something called a dot product. Okay. So we added vectors, we subtracted vectors. This is kind of like vector multiplication. So think about dot product as directional multiplication. So it's kind of weird. I mean, obviously we know 5 plus 5 plus 5 is 3 times 5. So it's kind of like that a little bit. It's applying the essence of one item to another. So let's go through the math first, and then Ms. York has an analogy that I'm gonna use. And she uses a Mario Kart. You guys play Mario Kart? Who plays Mario Kart for your like class and so in this room? No. For Spirit Week? No. Anyway, we'll talk about Mario Kart in a little bit. So typical multiplication, like 3 times 4, 3 grows by itself 4 times, right? Or it makes 3 4 times as large, right? You know, we know what that means, right? Now, the vector is grown in a direction. So you're growing the vector. That's what you're doing. And it's not a scalar, by the way. It's a little different because you're putting 2 vectors together, by the way. So it's not like, so remember we had this here, like if we had like, and you put in 2 on the outside, that's a scalar. That's not what we're doing. What we're doing instead is like, let's say I have these 2 different vectors here, right? And I do something called the dot product. That's kind of like vector multiplication. And apparently when you combine these two, they will grow in a certain direction. We'll talk about that when we get there. Adding vectors, right. You're accumulating the growth of several vectors. Multiply by constant, you make the existing vectors stronger, right? The dot product is this. You apply directional growth of one vector to another. The result is how much stronger we made the original vector. Okay, I'll do the analogy. I hope I don't butcher it. So Mario Kart, right? Like there's a thing called a boost, right? So someone explain Mario Kart to the class who knows Mario Kart well. Who knows Mario Kart really well? No one in this class knows Mario Kart?
Well, I don't.
Okay, Marie, why don't you explain Mario Kart to us? How's Mario Kart work? Okay, but then when you're playing, what happens? Okay, good. Yes, that's what I was looking here. Can you explain the boosters? Because you seem to know it. Yes. Yes.
That I'm not. I played the Tesla version more, but it's like basically the same. Like I forget which ones you have in Mario Kart, but you have like stuff where you can distract other opponents, or like you can like make yourself go to the front or something.
Okay, but then what happens with the booster?
Get a power. Beat up yourself and hurt someone else.
Okay, so you speed up yourself. Let's see. It's not about hurting people. let's speed up. Okay, so so the booster is one vector. So think of your direction of your cart as like a vector, right? It's going in a certain direction, and you got the booster as well, right? When you put those two together, then all of a sudden it goes really fast, right? And that's what a dot product is. A dot product is going to be how much impact. I know it seems kind of abstract. Let's do the math first, and it'll make more sense. But essentially, you're combining 2 vectors to make them an even bigger vector. Now, adding vectors can hurt each other, right? Because when you add it, like what if the wind is going against you, right? Then that could be reducing your magnitude or changing your direction. This is a little different. So here's the dot product. And here's how it looks. It's a really simple calculation, by the way. The calculation is really, really simple. So you get 2, 3, and 4, 7. So it's kind of like, okay, this is your Mario Kart, and that's your booster. And then when you actually apply the booster, it's going to be a number. So the dot product is always a number. Just so you know, it's not a vector. It's always a number. You multiply 2 with 4 and 3 with 7. So 2 times 4 is 8. 3 times 7 is 21. 8 plus 21 is 29. So and that's going to be like, and I got to talk to Ms. Zirkos analogy again because maybe I'm kind of butchering it, but essentially what you're doing is you're producing a scalar. So you combine those two vectors in this manner. Now, another way it could be thought of, excuse me, I'm losing my voice. Another way it could be thought of is this here. And we'll talk about this in a moment. But it can also be expressed this way as well. You take the magnitude of A times magnitude of B times the cosine of the angle between the two vectors. Because the vectors may not be in the same direction, right? So like let's look, so we have the blue and the purple, right? And there's a little angle between them, right? Obviously it's not that much different, there's a little angle between them. Actually 4, 7 I think is purple and 2, 3 is the blue. You can actually find the angle between the two vectors using the dot product. So 29 is going to equal that. Or 29 is going to equal, what's the magnitude of 2, 3? Mhm. What's the magnitude of 4, 7? Yep, you got it. Now, if you multiply it out, so I can use this to help me find the angle between two vectors also. So the dot product enables me to find the angle between two vectors. So cosine theta would equal 29 over 29.0689. By the way, the denominator should be larger than the top because cosine has to always be less than 1. If you solve for theta, it should be a super small angle. What's that angle going to be? Oh, geez, that's I'm in the degree mode. Yeah, we probably degrees probably makes more sense here.
And maybe a little note on the test for like, oh, and I'll put the calculator in this.
Yes, I'll do that. Yeah. So the dot product will help us to determine the angle between the two vectors. So it's kind of like your Mario Kart is like this purple, and that's a booster, and you apply the booster. You know, maybe the booster's in a different direction. That makes sense. You know, I don't understand Mario Kart either. You know, maybe I need to watch a YouTube video of Mario. I actually have an N64 in my house. I could probably maybe bring it. We could play during class. Yeah, maybe. You're good at it? Okay. Okay. So that's what's going on with the dot product. And we use that to help us find the angle between two vectors. And this calculation is super simple. You multiply the x's, multiply the y's, and add the results. So let's think of this one here. This actually, I think, might help you guys understand this a little better. Actually, Ms. Rick got a lot of good analogies. Okay, so let's kind of take a step back and read these on the Excuse me. So 3 comma 0, that's pointing to the left. 4 comma 0 also point to the left. So you have two vectors point to the left, one longer than the other, right? So 3 is a directional growth in a single dimension. 4 is directional growth also in the same direction. If you do the dot product, you get 12. Now, let's look at 3, 0, and 0, 4. 3, 0, and 0, 4. One is going left. Where's 0, 4 pointing? Up. So that's perpendicular. That's perpendicular, right? Dot product is 0. Okay, I think now I think I understand our analogy a little better. So the boosters for the Mario Kart thing? Are they the certain right? Like you use the booster when it's
No, just speeds you up.
okay, good. Yeah, because what if you're pointing? Yeah, what if the booster was perpendicular to your cart? Would you be able to move that?
I think I would still move the way you're moving.
Yeah, I'm messing with this. I'm messing with smart.
It makes you go fast or in directions you're already going. Yeah,
Got it,
or
okay.
it like distracts you.
Okay. Well, here's the deal. If your vectors are perpendicular, you have no dot product. The dot product is 0. It's kind of like if you were to. What's another good analogy I can think of? Yeah, hold on. Greek number means triple money. Wait, what?
Well, I mean, cosine of 90 is gonna be 0, so the answer is 0.
Yeah, I don't know what that means, but anyhow. But, okay, this analogy, potentially talked about.
I mean, it makes sense. The concept makes sense, but I don't get the destroy coffee and get rid of all your coffee. The other one will destroy all your money and you replace your coffee. You can both, you're gonna have nothing left.
Wait, so it's.
We're doing all of this to try to find an angle.
Yes, okay, so here's the deal. So cosine theta equals 0, right? If cosine theta equals 0, of course it has to be 90 degrees. If cosine theta equals 12, but your magnitude is going to be 12 also, right? The combination of the magnitude.
So let's do this, guys. Like, what if I set 12? Hold on, okay. What if I set so this is my dot product, right? So 12 will equal the magnitude of A times the magnitude of B times cosine theta. What's the magnitude of the first vector, guys? 3. What's the magnitude of the second vector? So 12 equals 3 times 4 times cosine theta. What's cosine theta equal? So your angle has to be 0. And that makes sense because both vectors go in the same direction. If they're both go in the same direction, what's the angle between them? 0. There's nothing, right? There's no gap between them. Now here, your dot product is 0. Your magnitude is still 3 and 4, but cosine theta has to be 0. Okay. So if that's the case, what's your angle going to be now? 90 degrees, or pi over 2. And that makes sense because 3, 0, and 0, 4 are clearly perpendicular. Oh, just visually, because 0, 4 goes like this, and 3, 0 goes like that. Yeah. So those are gonna be perpendicular. Well, if it was something weird, then you just do the inverse cosine. So, by the way, the word orthogonal, have you guys heard that word before? Okay, I'm gonna tell you right now, because the homework's gonna use the word orthogonal. Orthogonal means perpendicular.
Why did another word?
I don't know. Don't ask me. I didn't come up with the rules for math. But just so you know, that's something that you hear often, orthogonal. So I'll use perpendicular for you guys, sorry.
I feel like you made like this spot.
It could be. Okay. Let's keep going, guys. Okay. Okay, so she got more analogies here, but probably should bring her in to have her. Well, she teaches during C period. Maybe she'll maybe teach my. Actually, she taught you guys C period. Yeah, I should bring her back for C period. So addition, 3, 4, triple money, quadruple coffee. With dot product, we are mutating the original vector based on the rules of the second vector. So I'm not sure what she means by that. Destroy money, but quadruple. Oh, okay, because you have no. Got it.
Is this all on dot products?
Oh, I got it. Okay. Yeah, they cancel each other out. That's what's happening. Got it. Okay, I get it now. So you destroy. So this is a triple the money, but destroy the money, so they cancel out. Quadruple the coffee, destroy the coffee. So you got no coffee, got no money, you got nothing. Okay.
Well, you just
Okay. I think now I understand what she's saying. Okay, I think I get it now.
Why destroy?
Well, you stole it. What we're doing for a dot product.
What you're doing for a dot product is that vector A is broken down into its components, horizontal vertical components. Vector B is also broken down as horizontal vertical components. I'm multiplying the horizontal components together. I'm multiplying the vertical components together. Okay. And so what happens that when you combine it, so yeah, so like when we combine it, you do AX times BX plus AY times BY, it becomes a scalar value. Or just a number that we get.
Okay, here's like one more thing we're gonna talk about, and then we'll stop here on this page. Okay, this is just a proof. So so Ms. Zero came up with a proof.
This is just a proof, by the way. This is a proof. That's all it is. This is not a homework problem, right? Like, it's just a proof. What she did was she had vectors A and B. And if you decide to subtract the two vectors. So if you connect the so if you kind of reverse the other one that's negative B, obviously. And you connect, so like it's almost like doing this. Making that negative B. Remember we talked about connect tail one to the head of the other, and that's gonna be the resultant vector. So what if you want to find the magnitude of this? And that is what she's calling essentially the dot product. So if you think about it, do you guys recognize what this is? Anyone recognize what this is? Yes, good. Oh, Mr. Grant would be so proud of you. Yes, log cosine. Yes, C squared equals A squared plus B squared minus 2AB cosine angle C. Yes. So that's what's happening. So if you work, I'm trying to understand the math here. If you work all that out, well, we have little side notes. Okay. Yeah, that makes sense. Okay. Yeah, because you're taking the links of each of those. Got it. Okay. Okay. First. Okay. So you have that. So for the A minus B magnitude, yeah, if you were to boil that, okay. Correct. Okay. So if you try to find the magnitude of that, okay. You are getting that, all right. And then things should all cancel out nicely. So if you go through the process and cancel things out, you should stumble upon the dot product, which is that right there. I don't care if you know the proof or not. I think we'll give you guys that formula. I'm pretty sure, yeah, you know, it's up to me. I'll give you the formula.
So this basically means
It's just a wacko. It's a crazy proof.
about why
But-
this works.
Yeah. Well, the thing is that if you think about this, part I'm just a little stuck on. I guess a side that we have to pay attention to. If you multiply two vectors together. Sorry, if you do the dot product. Oh, actually, that does make sense. If you do the dot product of two vectors, it has to be V1 times V1 plus V2 times V2. That does make sense. And that is magnitude squared. That makes sense. Yeah. I get that now. Yeah, because the magnitude of vector V is going to be square root of V1 squared plus V2 squared. So when you square that, that goes away. That does make sense. So she's applying this side note to this over here. Okay, I got that now. And then she cleans it up and gets that. Got it. Okay. Anyhow, let's not worry about the proof. But what you do need to do is you need to be able to use that to find angle between two vectors. So the dot product, so essentially I'll put as a text box. The dot product divided by the two magnitudes multiplied together gives the cosine of the angle between two vectors. Yeah, so that's what it gives us. And the example on the next page at the top tells us that. And let me go pick up the homework, so I'll be right back.
Better on what? You know exactly what's going on there. I don't know what I know, it's wrong. The actual, well, you can go over it and then remember what you did. About like the road.
Okay, so your homework is gonna be anything that's highlighted in red.
So our notes.
Some of it's gonna be review of old stuff, that'll be the last week.
Yeah, well, if you post the answer key.
The answer key is provided for these, just so you know. Yeah, you guys are doing what's highlighted in pink / red, not green. Green will be the next homework after that.
Yeah, but my insurance like, I was like, oh, the double angle one, like, I like. You're like,
Yeah, one's a red's homework, and one in green will be the next homework after that. All right, we're all set. See you guys later.
Are those 14? Where's the?